Welcome. Settle in. Let your body relax and let the noise of the day fade into the background. Tonight, we are going to explore something you experience every single moment of your life, something so familiar that you almost never think about it, and yet so strange that it has puzzled the greatest physicists and philosophers for centuries. Tonight, we are going to talk about time. You feel time passing right now. You feel the seconds ticking by, one after another, carrying you forward from this moment to the next. It feels steady. It feels constant. It feels like a river, flowing in one direction, at one speed, carrying everything along with it. But what if that feeling is wrong? What if time is not at all what you think it is? Because here is the truth, nearly everything your intuition tells you about time turns out to be either incomplete or simply incorrect. Time does not flow at a constant rate. It can speed up and slow down. It is affected by gravity and by motion. The past and the future may not be as different as they seem. And at the deepest level of physics, time might not even be a fundamental part of reality at all. These are not wild speculations. These are conclusions drawn from some of the most rigorously tested theories in the history of science. And tonight, we are going to walk through them, slowly and gently, one idea at a time. There is no rush. After all, we have plenty of time. Or do we? Let us find out. Let us begin with the most basic question. What is time? It seems like it should have a simple answer. Time is what clocks measure. Time is the thing that separates yesterday from today and today from tomorrow. Time is what makes things change. But if you try to pin it down more precisely, it slips through your fingers. The philosopher Saint Augustine, writing more than 1600 years ago, said something that still resonates today. He wrote that if no one asks him what time is, he knows. But if someone asks him, he does not know. That captures the paradox beautifully. Time is the most familiar thing in the world, and yet it resists every attempt to define it. For most of human history, people thought of time as something absolute. It was a backdrop against which events played out, like a stage on which actors perform. Time was the same everywhere, for everyone, always ticking at the same rate, completely independent of anything happening within it. This was the view held by Isaac Newton, one of the greatest scientists who ever lived. Newton believed in absolute time, a universal clock that ticked identically for every observer in the universe. And for everyday life, Newton's view works perfectly well. Your clock and my clock agree. A second is a second. An hour is an hour. When you boil an egg for 10 minutes, it does not matter whether you are in London or Tokyo or on top of a mountain. 10 minutes is 10 minutes. Or so it seems. But in the early 20th century, a young physicist named Albert Einstein discovered something that shattered this comfortable picture. He discovered that time is not absolute. It is not the same for everyone. It is not a fixed backdrop. Time is flexible, stretchy, and deeply connected to the fabric of space itself. And that discovery changed everything. But before we get to Einstein, let us linger for a moment in the history of human thinking about time. Because long before physics gave us equations and experiments, philosophers and thinkers around the world were grappling with the mystery of time in ways that are still relevant today. The ancient Greeks had two different words for time. Chronos referred to sequential, measurable time, the kind we track with clocks and calendars. Kairos referred to the right moment, the opportune time, the qualitative experience of a moment that feels significant. This distinction hints at something important. Even thousands of years ago, people recognized that time as measured and time as experienced are not the same thing. The philosopher Heraclitus, writing around 500 years before the Common Era, famously said that you cannot step into the same river twice. Everything flows, everything changes, and time is the medium of that constant change. For Heraclitus, time and change were inseparable. Without change, there would be no time. Without time, there would be no change. His near-contemporary Parmenides took the opposite view. Parmenides argued that change is an illusion and that reality is timeless and unchanging. What appears to be change is merely the limited perspective of human beings, who cannot see the whole of reality at once. This view, remarkably, has echoes in the modern block universe theory that we will discuss later tonight. The idea that time is an illusion is not new. It is one of the oldest ideas in philosophy. In ancient India, Hindu and Buddhist thinkers explored cyclical views of time, in which the universe goes through vast cycles of creation, preservation, and destruction, each lasting billions of years. In this view, time is not a straight line with a beginning and an end, but an endless circle, repeating forever. This is a profoundly different way of thinking about time than the linear view that dominates Western thought, and it raises its own deep questions about the nature of existence and the meaning of change. These ancient perspectives remind us that the question of what time is has been with us for a very long time. Physics has given us powerful new tools for exploring this question, but the fundamental mystery remains the same. What is this thing we call time, and why does it seem to carry us forward so relentlessly? Let us see what modern physics has to say. Einstein's discovery came in two stages. The first, published in 1905, is called special relativity. The second, published in 1915, is called general relativity. Together, they form one of the most beautiful and revolutionary frameworks in the history of human thought. And both of them have profound things to say about the nature of time. Let us start with special relativity. Einstein began with a simple observation: the speed of light is the same for everyone. No matter how fast you are moving, no matter what direction you are traveling, when you measure the speed of light, you always get the same answer. About 186,000 miles per second. This might not sound surprising, but it has consequences that are deeply strange. Imagine you are standing on the platform of a train station. A train rushes past you at enormous speed. On the train, someone throws a ball toward the front of the car. From their perspective, the ball moves at, say, 10 miles per hour. But from your perspective, standing on the platform, the ball is moving at the speed of the train plus 10 miles per hour. The speeds add up. That makes intuitive sense. But light does not work that way. If the person on the train shines a flashlight toward the front of the car, you might expect the light to be moving at the speed of the train plus the speed of light. But it does not. The light moves at exactly the speed of light. Not a fraction faster. This is not a guess or an approximation. It is a measured fact, confirmed by experiment after experiment. For this to be true, something else has to give. And what gives is time itself. Einstein showed that time passes at different rates for observers moving at different speeds. The faster you move through space, the slower your clock ticks relative to someone who is standing still. This is not a mechanical effect. It is not that your clock is broken. Time itself is passing more slowly for you. This effect is called time dilation, and it is not just a theoretical curiosity. It has been measured directly, many times, with extraordinary precision. In one famous experiment, scientists placed extremely accurate atomic clocks on commercial airplanes and flew them around the world. When the clocks returned, they had fallen behind the clocks that had stayed on the ground. Not by much, just a few nanoseconds, but the difference was exactly what Einstein's equations predicted. time had literally passed more slowly on the moving airplanes. Let that sink in for a moment. The passengers on those airplanes aged slightly less than the people who stayed home. By an incredibly tiny amount, far too small to notice in everyday life, but it was real. Time is not the same for everyone. It depends on how fast you are moving. Now imagine pushing this effect to its extreme. If you could travel at 99% of the speed of light, time for you would pass at roughly 1/7 the rate of someone standing still. You could travel for what felt like a single year, and when you returned home, 7 years would have passed. At 99.9% of the speed of light, the ratio grows even larger. 1 year for you, more than 22 years for everyone else. And the closer you get to the speed of light, the more dramatic the effect becomes. At the speed of light itself, time would stop entirely. A photon, a particle of light, does not experience time at all. From the photon's perspective, if we can even use that word, its entire journey from creation to absorption happens in a single, timeless instant, even if that journey spans billions of light years. There is something quietly wonderful about this. The starlight reaching your eyes tonight left its star years or centuries or millennia ago. It has crossed vast stretches of empty space. But from the light's own perspective, no time has passed at all. The moment of its creation and the moment it reaches your eye are, for the photon, the same moment. Light exists outside of time. And it is light that allows you to see, to read, to experience the world. The very thing that connects you to reality is itself untouched by time. But speed is not the only thing that affects time. Gravity does too. And this is where Einstein's second great theory, general relativity, enters the picture. In general relativity, Einstein reimagined gravity not as a force pulling objects toward each other, but as a curvature in the fabric of space and time. Massive objects like planets and stars bend the fabric of space-time around them, and other objects follow the curves. When you drop a ball and it falls to the ground, it is not being pulled by a force. It is following the curved path that the Earth's mass has created in space-time. And here is the astonishing part: this curvature affects time. The stronger the gravitational field, the slower time passes. Near a massive object, like a planet or a star, time runs more slowly than it does far away in empty space. This is called gravitational time dilation, and like the time dilation from motion, it is a real, measured effect. Your feet, which are closer to the center of the Earth than your head, are in a very slightly stronger gravitational field. And because of that, time passes very slightly more slowly at your feet than at your head. The difference is absurdly small, far too tiny to notice, but it is real. It has been measured. Your feet are, in a very literal sense, younger than your head. This effect becomes dramatic near very massive objects. Near the surface of a neutron star, where gravity is billions of times stronger than on Earth, time would pass noticeably slower. And near a black hole, where gravity becomes so extreme that not even light can escape, time slows down enormously. If you could hover just outside the event horizon of a black hole and somehow survive, you might experience a few hours while centuries or millennia pass in the outside universe. This is not science fiction. It is a direct, mathematically precise prediction of general relativity, a theory that has been confirmed by every experiment ever designed to test it. Time is not a constant. It is shaped by gravity. It bends and stretches and warps, just like space does. In Einstein's universe, time is not a river flowing at a steady rate. It is more like a fabric, stretched tight in some places and slack in others, its pace determined by the mass and energy around it. Consider what this means for your experience right now. You are lying on the surface of the Earth, a massive ball of rock and metal and molten iron. Its gravity is bending space-time around you, gently curving the fabric of reality. Time is passing a tiny bit slower for you than it would if you were floating in deep space, far from any gravitational influence. You are, right now, in a slightly different flow of time than an astronaut orbiting above you, or a probe drifting between the stars. Time is not something that happens to you uniformly. It is shaped by where you are and how you are moving through the cosmos. And this shaping is not subtle at the extremes. In 2014, the movie Interstellar depicted astronauts visiting a planet near a supermassive black hole, where 1 hour on the surface was equivalent to 7 years back on their spaceship. This was not artistic license. The filmmakers consulted with the physicist Kip Thorne, a Nobel Prize winner, and the time dilation shown in the film was based on real calculations from general relativity. Near a sufficiently massive and rapidly spinning black hole, exactly this kind of extreme time dilation would occur. The universe really does allow for places where an hour can equal years. You might be thinking that all of this sounds very exotic, very far from everyday life. Black holes and neutron stars and airplanes flying around the world with atomic clocks. But in fact, you rely on the reality of time dilation every single day, whether you know it or not. But first, it is worth appreciating just how far we have come in our ability to measure time. For most of human history, timekeeping was rough and imprecise. Ancient civilizations used sundials, water clocks, and candle clocks, devices that could barely distinguish 1 hour from the next. The invention of the mechanical clock in medieval Europe was a revolution, giving people the ability to track minutes for the first time. The pendulum clock, invented by Christian Huygens in the 17th century, was accurate to about 15 seconds per day. Today, the best atomic clocks in the world are accurate to about 1 second in 30 billion years. That is longer than the current age of the universe. These clocks work by counting the oscillations of cesium atoms, which vibrate at an incredibly precise and stable frequency. In fact, the official definition of 1 second is now based on the cesium atom. 1 second is exactly 9,192,631,770 oscillations of a cesium-133 atom. Time, at the highest level of precision, is defined by the rhythms of the quantum world. And even more precise clocks are being developed. Optical lattice clocks, which use the oscillations of atoms trapped in lattices of laser light, are so sensitive that they can detect the difference in the flow of time between 2 points separated by just a few centimeters in height. With these clocks, you could literally measure the fact that time runs faster at the top of a staircase than at the bottom. That is how real time dilation is. It is not an abstraction. It is something that happens across the height of a single flight of stairs, and we now have instruments precise enough to measure it. The Global Positioning System, or GPS, the technology that tells your phone where you are on Earth, depends on a network of satellites orbiting the planet. Each satellite carries an extremely precise atomic clock, and your phone determines its position by comparing signals from multiple satellites and calculating the tiny differences in the time those signals were sent. For this to work, the clocks on the satellites need to be extraordinarily accurate. And here is the key: those clocks are affected by both types of time dilation. Because the satellites are moving quickly in their orbits, special relativity causes their clocks to tick slightly slower than clocks on the ground. But because the satellites are farther from Earth and therefore in a weaker gravitational field, general relativity causes their clocks to tick slightly faster than clocks on the ground. The two effects do not cancel out. The gravitational effect is larger, so the net result is that the satellite clocks run slightly fast compared to ground clocks, by about 38 microseconds per day. That might sound tiny, But if this correction were not applied, GPS positions would drift by about 10 kilometers per day. Your phone would think you were in a completely different part of the city. The system would be useless within hours. So every time you use GPS to navigate to a restaurant, find your way home, or track a delivery, you are relying on Einstein's theories of relativity. The engineers who built the GPS system had to account for the curvature of space-time to make it work. Time dilation is not an abstract concept. It is built into the technology in your pocket. So far, we have been talking about how time can speed up or slow down depending on motion and gravity. But there is another deep mystery about time that is quite different. It is the question of why time seems to flow in only one direction. Think about it. You remember the past, but you do not remember the future. Eggs break but do not unbreak. Ice melts in warm water, but warm water does not spontaneously form ice cubes. People grow older, never younger. There is a clear direction to time, from past to future, and we experience it as an unstoppable, one-way flow. Physicists call this the arrow of time. And here is what makes it so puzzling: almost all the fundamental laws of physics work equally well in both directions. If you filmed a collision between two billiard balls and then played the film backward, both versions would obey Newton's laws of motion perfectly. The laws themselves do not prefer one direction of time over the other. At the most fundamental level, the equations of physics are time-symmetric. So why does the universe have a clear direction in time? Why do we remember yesterday but not tomorrow? Why does disorder always seem to increase? The answer, as far as we understand it, lies in a concept from thermodynamics called entropy. Entropy is, roughly speaking, a measure of disorder or randomness in a system. A neatly stacked deck of cards has low entropy. A shuffled deck has high entropy. A glass of water with an ice cube in it has lower entropy than the same glass after the ice has melted and the temperature has equalized. The second law of thermodynamics states that in any isolated system, entropy tends to increase over time. Things tend to move from order to disorder, from structure to randomness, from low entropy to high entropy. This is why eggs break but do not unbreak. An intact egg is a low-entropy state, highly organized, with the shell, the white, and the yolk all in their proper places. A broken egg on the floor is a high-entropy state, disordered and mixed. The second law says that systems naturally move toward higher entropy. Going in the other direction, from broken to intact, is not forbidden by the laws of physics. It is just so overwhelmingly unlikely that it effectively never happens. The number of ways for an egg to be broken is astronomically larger than the number of ways for it to be intact. So the arrow of time, the reason you experience time as flowing in one direction, appears to be a consequence of entropy. The universe started in a state of extremely low entropy, highly ordered and structured, and it has been moving toward higher entropy ever since. That progression from order to disorder is what gives time its direction. Without it, past and future would be indistinguishable. But this raises another question. Why did the universe start in such a low entropy state? That is one of the deepest unsolved problems in physics. The Big Bang produced a universe that was remarkably smooth and uniform, a state of very low gravitational entropy. And as the universe evolved, gravity pulled matter together into clumps, forming stars and galaxies, increasing entropy. But why were the initial conditions so special? Nobody knows for certain. It is one of those beautiful mysteries that keeps physicists awake at night, which is perhaps ironic given that this video is designed to help you fall asleep. There is a certain poetry in the arrow of time. It is the reason why stories exist. Without a direction to time, there could be no narrative, no beginning, middle, and end. There could be no growth, no learning, no aging, no memory. The arrow of time is what makes your life a story rather than a static picture. It is what makes this moment different from the last one. And it arises not from the fundamental laws of physics, which are perfectly happy to run in either direction, but from the simple, statistical fact that there are overwhelmingly more ways for things to be disordered than ordered. Your life, your memories, your sense of past and future, all of it rests on the foundation of entropy, quietly and relentlessly increasing, giving time its shape and its direction. Let us go deeper still. We have been talking about time as something that flows, that passes, that moves from past to future. But some physicists and philosophers have argued that this picture of flowing time is an illusion. That time does not flow at all. This idea comes from taking Einstein's relativity seriously. In special relativity, the concept of now is not absolute. Two observers moving at different speeds will disagree about which events are happening at the same time. What is now for you might be in the future for someone else and in the past for a third person. There is no universal present moment that everyone shares. This leads to a view of reality called the block universe. In the block universe, the past, present, and future all exist equally. Time is like a dimension, similar to the three dimensions of space. Just as all points in space exist simultaneously, all moments in time exist simultaneously. The universe is a four-dimensional block, with time as one of the dimensions, and every event that has ever happened or will ever happen is already there, frozen in the fabric of space-time. In this view, the feeling that time flows is something like an illusion created by our consciousness. We experience one moment at a time, like a spotlight moving along a film strip, but the entire film strip already exists. The past has not disappeared. The future has not yet to be created. They are all there, all equally real, all coexisting in the block of space-time. This is a deeply unsettling idea for many people. It seems to conflict with our most basic experience of reality, the sense that the present is special, that the past is gone, and that the future is open and undetermined. But the mathematics of relativity supports it. And many physicists, including Einstein himself, found a certain peace in the idea. After the death of his close friend Michel Besso, Einstein wrote in a letter that the distinction between past, present, and future is only a stubbornly persistent illusion. He seemed to find comfort in the thought that his friend's life still existed, in some sense, in the fabric of space-time. You do not need to decide tonight whether the block universe is the correct view of reality. It is one of those ideas that sits at the boundary between physics and philosophy, and brilliant minds disagree about it. But it is worth sitting with for a moment, as you lie here in the dark. The idea that every moment of your life, every experience you have ever had, every sunset you have watched, every conversation you have enjoyed, still exists somewhere in the fabric of time. Nothing is truly lost. Some philosophers have pushed back against the block universe, arguing for what they call presentism, the view that only the present moment is real. The past has ceased to exist, and the future does not yet exist. In this view, the present is ontologically special, not just experientially special. The debate between the block universe and presentism is one of the most active areas in the philosophy of time, and it touches on questions that go far beyond physics. It touches on questions about free will, about the nature of identity, about what it means for something to be real. If the block universe is correct, then in some sense, every version of you that has ever existed still exists. The child you were, the teenager, the person you were last Tuesday morning. They are all there, embedded in the fabric of space-time, as real as the person lying here right now. And the future versions of you, the person you will be tomorrow and next year and decades from now, are also already there, waiting to be experienced. This is either deeply comforting or deeply unsettling, depending on your temperament. But either way, it is a remarkable idea, one of the most extraordinary implications of taking Einstein's physics seriously. Now let us travel to the other end of the scale, from the vast stretches of space-time to the unimaginably small world of quantum mechanics. And here, time becomes stranger still. In quantum mechanics, the physics that governs atoms and subatomic particles, time plays a peculiar role. Unlike position or momentum, which are represented by mathematical operators that can have uncertain or probabilistic values, time in quantum mechanics is treated as a fixed background parameter. It is the stage on which quantum events play out, not one of the actors. This asymmetry has puzzled physicists for decades. There are also quantum phenomena that seem to challenge our ordinary understanding of time. One of the most famous is quantum entanglement. When two particles become entangled, measuring one of them instantly affects the state of the other, no matter how far apart they are. This happens instantaneously, as if the connection between the particles does not care about the distance or the time it would take light to travel between them. Einstein was deeply uncomfortable with entanglement. He called it spooky action at a distance. But experiment after experiment has confirmed that it is real. Entangled particles do appear to influence each other instantaneously, across any distance. This does not allow faster-than-light communication, for subtle and important reasons, but it does suggest that the relationship between time, space, and causality at the quantum level is more complex than our everyday experience suggests. There is also the question of the quantum arrow of time. At the fundamental level, the equations of quantum mechanics, like those of classical mechanics, are time-symmetric. They work equally well running forward or backward. And yet, when we make a quantum measurement, something irreversible seems to happen. The wave function, which describes all the possible states a particle could be in, appears to collapse into a single definite state. This collapse seems to introduce a direction to time, a before and after, that is not present in the underlying equations. What causes this collapse, and whether it is even real, is one of the great unresolved debates in quantum physics. These are deep waters, and we do not need to swim to the bottom tonight. The point is simply this: at the smallest scales of reality, time is not the simple, straightforward thing it appears to be in everyday life. It is woven into the fabric of quantum mechanics in ways that we are still struggling to understand. And that struggle is one of the most exciting frontiers in modern physics. There is another way to think about time that is closer to home. Not time as physics describes it, but time as your body lives it. Because your body has its own deep relationship with time, one that has been shaped by billions of years of evolution. Every cell in your body contains molecular clocks. These are not metaphorical clocks. They are actual biochemical oscillators, loops of proteins that are produced and degraded in cycles that repeat roughly every 24 hours. These are your circadian rhythms, and they govern an astonishing range of bodily functions: when you feel sleepy, when you feel alert, when your body temperature rises and falls, when certain hormones are released, when your immune system is most active. Your body is not just existing in time. It is keeping time, measuring it, responding to it at the molecular level. These internal clocks are synchronized to the external world primarily by light. When light enters your eyes, specialized cells in your retina send signals to a tiny region of your brain called the suprachiasmatic nucleus, which acts as the master clock for your entire body. This is why jet lag feels so disorienting. Your internal clocks have been set to one time zone, but the light signals are now telling them something different. It takes several days for all your internal clocks to resynchronize, and during that time, you feel out of step with the world. There is also the question of aging, which is perhaps the most personal way we experience the passage of time. Why do we age? At the cellular level, aging is driven by the accumulation of damage to DNA, the shortening of telomeres, the protective caps on the ends of chromosomes, the buildup of misfolded proteins, and the gradual decline of cellular repair mechanisms. Time, at the biological level, is a slow process of accumulating disorder, remarkably similar to the increase of entropy that drives the arrow of time in physics. Some organisms seem to defy this process. Certain species of jellyfish can revert to an earlier stage of their life cycle, effectively resetting their biological clock. Some tortoises and whales show negligible senescence, meaning they do not appear to age in the way that most animals do. These organisms remind us that aging is not an inevitable consequence of the laws of physics. It is a biological process, shaped by evolution, and it is at least theoretically possible to slow it down or even reverse it. Time passes for these creatures just as it does for us. But their bodies respond to that passage differently. As you lie here tonight, your body is doing extraordinary things with time. Your brain is consolidating memories from the day, sorting through experiences and deciding what to keep and what to discard. Your cells are repairing damage, producing new proteins, clearing away waste. Your immune system is on patrol, more active now than during the day. Sleep is not a passive state. It is one of the most time-intensive activities your body performs. And it is happening right now, as time continues its quiet passage. Let us step back from the equations for a moment and consider something more personal. How do you experience time? Not how does physics describe time, but how does it actually feel to you, right now, lying here in the dark? Time feels like it flows. It feels like the present moment is special, a moving boundary between the fixed past and the open future. It feels like it moves at a certain pace, sometimes fast, sometimes slow, depending on what you are doing and how you are feeling. But here is the thing, that feeling of time flowing is created entirely by your brain. And your brain is not a reliable clock. You have probably noticed that time seems to pass quickly when you are absorbed in something you enjoy, and slowly when you are bored or anxious. An hour at a party can feel like 15 minutes. An hour in a waiting room can feel like an eternity. This is not just a subjective impression. Neuroscientists have shown that the brain's perception of time is genuinely flexible, shaped by attention, emotion, memory, and even body temperature. When you are in danger, time seems to slow down. People who have been in car accidents or falls often report that everything seemed to happen in slow motion. For a long time, scientists thought this meant the brain was actually processing information faster during moments of terror. But experiments have shown that this is probably not the case. Instead, what seems to happen is that the brain forms much denser memories during frightening experiences, and when you recall the event later, the richness of the memory makes it feel like it lasted longer than it actually did. Your brain also has multiple internal clocks, not just one. Different regions of the brain track time at different scales. Some handle the millisecond timing needed for coordinating movement and processing speech. Others handle the seconds to minutes timescale needed for conscious experience. And still others handle the circadian rhythms that govern your sleep-wake cycle over the course of a day. These systems do not always agree, and their disagreements contribute to the sometimes strange and fluid quality of your experience of time. And there is something else. Your experience of now, this present moment that feels so vivid and immediate, is not actually instantaneous. The brain takes time to process sensory information, roughly a few hundred milliseconds. What you experience as now is actually a slightly delayed, heavily processed construction, a story your brain is telling you about what happened a fraction of a second ago. You are never truly experiencing the present. You are always experiencing the very recent past, assembled into a seamless narrative by the remarkable machinery of your brain. This is not a flaw. It is a feature. Your brain constructs a stable, coherent experience of time from the chaotic flood of sensory data it receives, and it does so with extraordinary skill. But it means that your subjective experience of time is, in some sense, an elaborate illusion, a model built by the brain, not a direct perception of reality. The flow of time that feels so real, so undeniable, is something your mind creates. And this model can be disrupted. Certain drugs can make time seem to stretch or compress dramatically. Meditation practitioners often report a profound alteration in their sense of time, a feeling that the present moment expands and the usual rush of past and future recedes. People with certain neurological conditions experience time very differently from the rest of us. Some feel that time has stopped entirely. Others feel that events from the past are happening right now. These experiences remind us that our normal sense of time, which feels so solid and reliable, is actually a delicate construction that depends on the proper functioning of specific brain regions. Even the simple act of falling asleep changes your relationship with time. In deep sleep, your sense of time effectively disappears. Hours can pass in what feels like an instant. You close your eyes, and when you open them, the night has gone. Where did that time go? It was not experienced. It was not perceived. And yet it passed. Your body continued its processes, your cells continued to divide, the earth continued to turn. Time moved forward, but you were not there to witness it. This might be the most intimate demonstration of the fact that your experience of time and time itself are two very different things. This brings us to perhaps the most radical question of all. Does time actually exist? It might seem absurd to ask. Of course time exists. You can feel it passing. You can measure it with clocks. You can see its effects in the aging of your body and the changing of the seasons. How could time not exist? But some physicists have argued that at the most fundamental level, time might not be a basic ingredient of reality. It might be what physicists call an emergent phenomenon, something that arises from deeper, more fundamental processes, much like temperature emerges from the motion of atoms. Temperature is real, in the sense that you can feel it and measure it, but it is not a fundamental property of individual atoms. It is a collective property that emerges when many atoms interact. Time might be similar. One of the most prominent advocates of this idea is the physicist Carlo Rovelli. In his work on quantum gravity, Rovelli has explored the possibility that the fundamental equations describing reality do not contain time at all. Instead, they describe relationships between things, and what we call time is a way of organizing those relationships that emerges at larger scales. At the deepest level, there is no flowing river of time. There are only correlations between physical variables, and our brains interpret those correlations as a sequence of events unfolding in time. This is related to a deep problem in physics called the problem of time. When physicists try to combine general relativity, which describes gravity and the large-scale structure of space-time, with quantum mechanics, which describes the behavior of atoms and subatomic particles, they run into a fundamental conflict. In general relativity, time is dynamic, flexible, and intertwined with space. In quantum mechanics, time is a fixed background parameter. When you try to merge the two, the equations seem to suggest that time disappears entirely. The resulting equation, called the Wheeler-DeWitt equation, describes the quantum state of the entire universe, and it contains no time variable at all. The universe, at this fundamental level, appears to be timeless. Not all physicists agree with this interpretation. The problem of time is one of the most debated and unresolved issues in theoretical physics. But the very fact that it is being seriously discussed by leading researchers shows just how far our understanding of time has come from the simple, intuitive picture of a universal clock ticking steadily in the background. And now, let us talk about something that has captured the human imagination for over a century. Time travel. The first thing to say is that you are already a time traveler. You are traveling into the future right now, at a rate of 1 second per second. That might sound like a joke, but it is actually more profound than it seems. Because as we have discussed, that rate is not fixed. By moving very fast or by being near a very massive object, you can change the rate at which you travel into the future. In a very real sense, the astronauts aboard the International Space Station are time travelers. They return to Earth having aged very slightly less than the people who stayed behind. But what about traveling further into the future? In principle, this is entirely possible according to the known laws of physics. If you could build a spacecraft capable of traveling at close to the speed of light, time dilation would allow you to reach the distant future. You could travel for what feels like a year and return to find that decades or even centuries have passed on Earth. This is not speculative. It is a direct consequence of special relativity, confirmed by countless experiments. Traveling into the past, however, is a very different matter. General relativity does allow for theoretical solutions that involve travel to the past. These involve exotic structures in space-time, like wormholes, which are hypothetical tunnels connecting distant points in space-time, or closed time-like curves, which are paths through space-time that loop back on themselves. But these solutions typically require exotic forms of matter or energy that may not exist, and they raise paradoxes, like the famous grandfather paradox, in which a time traveler goes back and prevents their own birth, creating a logical contradiction. Most physicists believe that some mechanism, perhaps one we have not yet discovered, prevents travel to the past. The physicist Stephen Hawking called this the chronology protection conjecture, the idea that the laws of physics conspire to prevent time travel to the past. But the truth is that we do not know for certain. The question of whether backward time travel is possible remains open, one of the many tantalizing mysteries that time presents to us. For now, though, let us set aside time machines and wormholes. The real marvel is what we already know. Time is not what it seems. It is flexible, relative, shaped by gravity and motion, deeply intertwined with space, and possibly not even fundamental to reality. That is more than enough wonder for one night. But there is one more thought worth having about time travel, and it is a gentler one. In a sense, we are all time travelers into the past every time we look at the night sky. The light from the nearest star beyond our Sun, Proxima Centauri, takes about 4 years to reach us. When you look at that star, you are seeing it as it was 4 years ago. The light from the Andromeda Galaxy, visible on a clear night as a faint smudge, left that galaxy about 2.5 million years ago, when our ancestors were just beginning to walk upright on the African plains. And the light from the most distant galaxies we can observe left them over 13 billion years ago, when the universe was young and the first stars were just beginning to shine. Every time you look up at the night sky, you are looking into the past. The further you look, the further back in time you see. The universe is a natural time machine, and all you need to use it is a clear night and a pair of eyes. That is a beautiful thought to carry with you as you drift towards sleep. Before we close, let us take one last, long look at time from the widest possible perspective. What does the future of time itself look like? The universe is about 13.8 billion years old. It has been expanding since the Big Bang, and as we discussed in our first episode, that expansion is accelerating, driven by the mysterious force of dark energy. If this acceleration continues, and there is every reason to believe it will, the universe will continue to expand forever, growing colder and emptier with each passing eon. Stars will continue to form for a while, but eventually the raw materials will run out. The gas clouds from which stars are born will be used up or dispersed, and the era of star formation will come to an end. The last stars will burn through their fuel and die, leaving behind white dwarfs, neutron stars, and black holes. The universe will grow dark. Over unimaginable stretches of time, even these remnants will fade. White dwarfs will cool to black, invisible cinders. Neutron stars will spin down and grow silent. Black holes will slowly evaporate through a process called Hawking radiation, shrinking over trillions upon trillions of years until they finally vanish in a faint puff of particles and radiation. And then? Then there will be nothing left but a thin, cold soup of scattered particles, drifting farther and farther apart as space continues to expand. The temperature of the universe will approach absolute zero. Nothing will happen. Nothing will change. This is what physicists call the heat death of the universe, the ultimate state of maximum entropy, the final, quiet end of all structure and activity. In that final state, time will still technically exist, in the sense that the equations of physics still contain a time variable. But with nothing happening, no events, no changes, no processes, time will become meaningless. There will be no way to distinguish one moment from another. The universe will be, in a very real sense, timeless. But that is incomprehensibly far in the future. So far that the current age of the universe is not even a rounding error by comparison. Right now, the universe is young and vibrant, full of stars and galaxies and planets and life. Time is rich with events, with changes, with stories being told and experiences being had. Including this one. Including you, lying here, listening to these words, as time gently carries you towards sleep. And there is a strange comfort in knowing the full arc of time. You are here, in this brief, extraordinary period when the universe is alive with complexity and light. Billions of years from now, the stars will be gone. But right now, they are here. Right now, time is full and rich and meaningful. You exist in a privileged window of cosmic history, a time when there are things to see, things to feel, things to wonder about. That is not a small thing. That is, in fact, the most remarkable thing of all. So what have we learned tonight? We have learned that time is not what it seems. It is not a fixed, universal constant, ticking away at the same rate for everyone. It speeds up and slows down, shaped by motion and gravity. It is woven into the fabric of space, forming a four-dimensional tapestry called space-time. It may not flow at all if the block universe picture is correct. Your experience of its passage is a construction of your brain, a story told to you by your own neurons. And at the deepest level, time might not even be a fundamental part of reality. And yet, for all of that, time is deeply, undeniably real in the way that matters most. It is the medium of your life. It is the space in which you love, and learn, and grow. Every moment you experience, every memory you cherish, every hope you hold for the future, exists within time. Whatever time ultimately turns out to be, it is the stage on which everything meaningful happens. There is something profoundly humbling about contemplating time. It connects you to the past and to the future, to the first moments of the universe and to its eventual, quiet end. Every second you experience is part of an unbroken chain stretching back to the Big Bang and forward into an unimaginably distant future. You are a brief, beautiful pattern in the fabric of time, a pattern that has never existed before and will never exist again. Think about the sheer improbability of this moment. The atoms in your body were forged in ancient stars. They drifted through space for billions of years, became part of a spinning disk of gas and dust, were incorporated into a planet, and eventually, through an unbroken chain of chemical reactions stretching back nearly 4 billion years, they became part of you. A being that can contemplate the nature of time itself. The universe spent nearly 14 billion years preparing for this moment, the moment you lie here, breathing quietly, thinking about what time really is. That is not a small thing. And here is perhaps the most beautiful thought of all. Of all the ways to spend time, of all the things the universe could be doing with its brief window of complexity and light, it is doing this. It is thinking. It is wondering. It is asking questions about its own nature. Through you, through your brain, through this very moment of quiet contemplation, the universe is exploring the mystery of time from the inside. You are the universe's way of trying to understand itself. Let your thoughts slow now. Let the ideas from tonight settle into your mind like leaves settling on still water. You do not need to hold on to any of them. They will be there in the morning if you want them. Time is passing, as it always does. But right now, in this moment, you have nowhere to be and nothing to do. The past is behind you. The future will take care of itself. All that exists is this present moment, this breath, this heartbeat, this gentle voice carrying you towards sleep. Whether time flows like a river or stands still like a block of ice, whether it is fundamental or emergent, whether your experience of it is real or constructed, one thing is certain. This moment is yours. And it is enough. Let your breathing deepen. Let your muscles relax. Let the weight of your body press into the bed beneath you. The universe has been unfolding for nearly 14 billion years, and it has brought you to this exact moment, this exact place, this exact breath. There is nowhere else you need to be. There is nothing else you need to understand. Time will carry you from here. Into sleep. Into dreams. Into whatever comes next. And whatever that is, it will unfold at exactly the pace it is meant to. Perhaps tonight, as you drift off, you will dream of clocks melting like the paintings of Salvador Dali. Or of standing near a black hole, watching centuries pass in the blink of an eye. Or perhaps you will dream of nothing at all, and time will simply vanish, as it always does when sleep takes hold. And when you wake, it will feel like no time has passed at all, or like an eternity has gone by. Either way, time will be waiting for you, ready to carry you through another day. You are a brief, luminous pattern in the fabric of time. Cherish it. But not tonight. Tonight, just rest. Close your eyes. Let time do what it does. And rest. Good night.